Item B, intrinsic geometry, exterior algebra in 3D. So this can be for any D, okay, any dimension, no problem. So B part 1, manifold. B part 1, lecture 13, transition function. You see, this concept that's written here, you already have been seen. You see that, so no news, okay, about the concept over here. But that's established what is a transition function. To obtain in the transition function between charts u and v, consider the following steps. Step 1, let's mark over here. Step 1, definition of the mappings. In this case, we consider a three-dimensional differentiable manifold M3 and define mapping. You see, 1, mapping alpha sub x. You see, there's a map. Okay, this map M3 to the Euclidean space R3. Alpha x acting on P, this leads to the point of Q, what I called phi1, phi2, and phi3, where phi I, for I is equal 1, 2, 3, okay? This case, you see, the Cartesian coordinate of the point Q in R3. You see, this is R3 over here, R3. See, that's M3, okay? This is a linear mapping. Now, P, attention now, the coordinates of P, these are x1, x2, and x3, belongs to the manifold, you see? But this is in the Euclidean coordinates, the curved surface, x1, x2, x3 is a point P that belongs to the manifold. Remember that the point P can be obtained through this gamma function here. Lambda is a scalar, x1 of 0, x2 of 0, x3 of 0, because lambda is equal to 0. And there is a region here between plus epsilon and minus epsilon, as we presented in previous videos. Now, this is 2. Okay? Step 1, item 2. Inverse mapping alpha x minus 1. The inverse matrix of x minus 1 defines a chart U around point P, belong to the manifold. You see, now is the inverse. You see, you have a point Q here, and then you apply alpha x minus 1, then leads to a point in the manifold. But you choose points around Q. You see, for points closer, okay, and around Q, you see, these points will be Q1, x2, x3, are the local coordinates in the chart U. You see, now you apply the inverse linear mapping. You see, you let a lot of points around Q, then you applied the inverse, and then this is a region over here, or around P, okay, which is the chart U. Attention now, the chart U, the coordinates x1, x2, and x3 belongs to the manifold, okay? And as I emphasized a lot, you see, these points in the small region around P can be approximated to the tangent vector space. You see, I always say clearly because there are a lot of confusion in the literature, you see. So, now, this point here belongs to the manifold, okay? But if I use the tangent vector space, x1, x2, and x3, okay, you'll be approximated to the tangent vector space. Okay, number 3, item 3 here. Analogous for mapping alpha y, you see alpha sub y. What I did here for alpha x is the same. So I create on the same point P a new coordinates. You see, here before is x1, x2, x3. Now here is y1, y2, y3 belong to the same point P, the same point P, okay? This is defined by another mapping, alpha y, M3 to R3. So I bring back from here to here, but this will be not a point Q, to be a point Q prime, which the coordinate are C1, C2, and C3. Exactly what I did here, okay? So alpha I map M3 to R3, and this is another point Q prime, you see? Not Q, it's Q prime, where C1, C2, and C3, in this case, are the Cartesian coordinate of Q prime in R3. I create another point over here, you see? That's number 4. Inversing mapping alpha y minus 1 exactly is analogous what I did for alpha x minus 1. Okay, the inverse I choose on around point Q prime, you see, points around Q prime, then apply this inverse mapping that brings points around Q prime. You see points, you see here, for points closer and around Q prime. You bring back to the manifold, you see. Now, then I create another chart in which P is in the intersection of these two charts, U and V, as I will show ahead. So then I have points y1, y2, and y3. Now, step 2. Now it's coming transition function. Between chart U and V, since P belongs to both chart U and chart capital V, you see, we can express the same point using either coordinate system. Chart U, the coordinate system, in this case, is x1, x2, x3. Euclidean. Chart V, y1, y2, y3. Now, if I use, attention now, if I use the chart, this point over here is important here, they are approximate. Approximate points. You see, the chart is a place, is a region in which I work, because in the chart points are Cartesian points. It's approximated. You see the tangent vector space when I use the chart U and V. Now, to find relation between xi and yi, consider the composition, okay? Alpha y minus 1, okay, composed with alpha x, brings point from R3 to R3. You see, that's important here. That's a place where I can work, you see, because they are not point on the manifold anymore. You see, that's clear. This function maps coordinates, you see, x1, x2, x3. In chart U, attention now, this point here, okay? They are approximated. Approximated. See? Approximate from the manifold to the tangent vector space. Okay? Now, in this case, again, this function maps coordinates in chart U to coordinates y1, y2, i3, approximated. Approximated. Okay? That is, y is a function of x1, x2, and x3. You see, because they belong to the same point P. So I can get this relation over here. Okay? That's a function. Now, point Q, you see, is a function of phi I is equal 1, 2, 3. Now, here, you see, point Q prime, if I is equal 1, 2, 3. You see, this is alpha x, alpha I, and then, look, I just set over here for you for more clarity. I just have these two regions, U and V. P here inside, you see, is a point which is the point that belongs to the blue V and the green U. You see, that's point Q and point Q prime. You see clear here. You see, this over here, okay, is a region which I will map back to the manifold. You see this alpha x minus 1. This is alpha y minus 1. So this is clear what I said over here before. Okay? Now, I prepared in next lecture 14 a numerical example. You see, just to apply all is written over here. Okay? You see clearly how to obtain these functions. You see, I will consider a numerical mapping. You see that. That's a very, very interesting.